This is the fourth lecture of the course MTH 204A for section B. In the third lecture, we have been introduced to solvable groups. In this lecture, we will view solvable groups from a slightly different perspective. And in fact, we will be proving a famous theorem called the Jordon-Holder theorem. We begin this lecture with a group G. By a tower of subgroups of G, we mean a finite and nested sequence of subgroups of G, that is a finite sequence of this form. Here, from the second term onwards, every term has to be contained in its immediate predecessor. Okay. So given a tower of subgroups of G, we say the tower is normal if each Gi plus 1 is a normal subgroup of Gi for every I from 0 to n minus 1. So that is each term, of course the second term onwards, each term in that sequence will be a normal subgroup of its predecessor. Please note that we do not insist that each Gi has to be a normal subgroup of G. That we do not insist. The only thing we insist is each Gi plus 1 has to be a normal subgroup of Gi. If a tower of subgroups of G is normal, then we write this, and it makes sense to consider the factor groups Gi modulo Gi plus 1 for each I. So these factor groups are called the factors of this tower. Given any tower, irrespective of normal or not, the number of strict inclusions is called the length of the tower. It's easy to see that when the tower is normal, then the length is nothing but the number of non-trivial factors of this tower, because this factor group is trivial if and only if the inclusion, the inclusion is not proper, that is there will be an equality. Okay, let's look at some quick examples. So the first example is from S4. So S4 has the normal subgroup A4, and inside A4 we do have a normal subgroup of order 4 which is isomorphic to the Kleins 4 group. Hence, apart from identity, if we take any non-identity element, let's say this, then that will give us a subgroup of S4 which is normal inside this, and thus we obtain a normal tower in S4. The next example is regarding the dihedral group D8. Recall that the dihedral group is generated by a rotation and a deflection. So the group of rotations has index 2. So therefore this is normal, and since this is a cyclic group of order 4, if we pick R square, then 1 R square will be a subgroup of order 2, hence it is normal in this, since this is abelian, so being a subgroup of this abelian group, this is normal, and thus we obtain a normal tower in D8. The third example is somewhat general. So recall that given any group, we can talk about its derived subgroups. So for any n, if we can consider the derived subgroups up to the nth stage, for any n, if we consider the derived subgroups of G up to the nth stage, then that gives us a normal tower. And the normality is because for any group G, its derived subgroup is a normal subgroup of G. So from that, the normality of this tower is immediate. The next exercise, the following exercise gives us a normal tower in the general linear in the linear group of all invertible upper triangular matrices. So let's take F to be the field of rationals, reals or complex, and n be a natural number. So G be the general linear group, that is the group of all invertible n by n matrices with entries from F. Then we consider the subgroup of all upper triangular invertible matrices, and furthermore we consider the further subgroup of all invertible diagonal matrices. Now we denote the collection of all strictly upper triangular matrices. So note that this cannot be invertible. So that collection is we denote this by n, and define for every r greater or equal to 2, n r minus 1 is we define n r minus 1 to be the collection of all matrices of this form. So basically when r is 2, then n1 is nothing but n1 in a typical matrix belonging to n1, all the entries belonging to the diagonal and below the diagonal will be 0. So n1 is nothing but our n, that is the collection of all strictly upper triangular matrices. Then for n2, basically it will so of course along the diagonal everything will be 0, and so for the entries lying below the diagonal. Next a12 will also be 0, then a23 will also be 0. So the first possible non-zero entry will start from a13, then and that's how, so basically then it will look a13, a23 and so on, and the rest of course can be anything. So so for any r greater or equal to 2, n r minus 1 denotes the collection of all matrices of this form, n by n matrices. And then we define ur for any r from 1 up to n as follows, that is with all the matrices lying in nr, if we add the identity matrix. So again let me repeat, so with every matrix in nr, I'm adding identity matrix to that, and after doing this, the collection that we obtain is denoted by ur. Now it's a routine verification that ur defined so above is a subgroup of T. Let me remind you that T is the invertible collection of all invertible upper triangular matrices. It's a group with respect to matrix multiplication. So ur is a subgroup of T, and u1 is a normal subgroup of T. So in order to show ur is a subgroup of T, it's enough to show that each matrix lying in ur is invertible. And the next thing is for any r from 1 up to n minus 1, for each r from 1 up to n we have a subgroup ur. So therefore we have ur minus 1, so up to u1. So the second part of this exercise says that each ur plus 1 is a normal subgroup of ur, and the factor group is isomorphic to the additive group of f n minus r, that is the so this is the collection of all n minus r tuples from F. Of course, this is a vector space over F, but here we consider only the additive group of that. So this factor group is isomorphic to that. So in view of these two, it is now immediate that this is a normal tower in the group of invertible upper triangular matrices. Okay. Given a normal tower, we say it is abelian if each factor group gi modulo gi plus 1 is abelian. Furthermore, we say a normal tower is cyclic if each factor group is cyclic. So let me look at these examples once again. So here the first factor group is z modulo 2z. This is of course a z modulo 2z which is cyclic. Now here this is z modulo 3z, and again the third quotient is Z modulo 2Z. So therefore this is an example of an abelian tower, and of course in fact cyclic. This is also an example of a cyclic tower. And now if we look at this for any n, this may not be cyclic, however this is abelian, because for any group we have already seen that G modulo its commutator subgroup is an abelian group. So the third one is an example of an abelian tower, though it may not be cyclic. So thus we have seen that given any group G, there is a natural abelian tower it has, namely for any n, the tower of derived subgroups up to nth stage. So so given any group, there is an abelian, it possesses an abelian tower with n terms. Conversely, conversely observe that if we are given an abelian tower in G with n terms, then the following happens. So since the tower is abelian, so G modulo G1 is abelian, therefore G1 must contain the first derived subgroup of G. Similarly this G2, which is the derived subgroup of G1, the second derived subgroup is the second derived subgroup of G, which is the derived subgroup of the first derived subgroup of G. So this has to be contained in G1 prime, because like here G2 modulo, G1 modulo G2 is abelian, so therefore G2 must contain the derived subgroup of G1, and derived subgroup of G1 contains the second derived subgroup of G. Therefore we obtain that G upper 2 is a subgroup of G2, and continuing in that manner we see that the nth derived subgroup of G is a subgroup of Gn. So let me again repeat that if we are given an abelian tower in G with n terms, then from that it follows that the derived subgroups of G up to the nth order, those derived subgroups are contained in the corresponding terms of that abelian tower. So in particular, if the end term of the last term of this abelian tower is identity, so if this is identity, then it forces the nth derived subgroup of G to be trivial. I repeat, so since each Gi is a subgroup, since for each I the ith derived subgroup is a subgroup of G is a subgroup of Gi for each I from 1 up to n. So from that it follows that if this is trivial, then the nth derived subgroup of G has to be trivial, that is G has to be solvable. So thus what we have seen here is, if we are given an abelian tower in G ending with the trivial subgroup, then the group has to be solvable. In fact, the following theorem shows that this is a necessary and sufficient condition for solvability of a group. So the theorem is exactly what I have just said. For any group G is solvable if and only if it admits an abelian tower ending with the trivial subgroup. The proof is all I have almost discussed just now. So let's if we assume G is solvable, then we know that for some n Gn is trivial. So therefore this is going to give in that case this is going to give me an abelian tower in G ending with the trivial subgroup. And conversely, if we are having an abelian tower with ending with the trivial subgroup, then the discussion what we have just made shows that nth derived subgroup of G has to be trivial, that is G is solvable. So thus we have proved this theorem. Now we talk about another abelian tower associated to any group G. So in the literature it is called the upper central series of a group. So let me again tell you that given any group we have a natural abelian tower associated to that, namely if we consider, I mean for any n, if we go up to the n, and if we consider the derived subgroups of G up to the stage n, then that gives me an abelian tower with n terms. So given any group we do have an abelian tower, the tower of successive derived subgroups. Now we are going to talk about another abelian tower which is associated to any group G. So this is called the upper central series of the group. So for any group G we define a chain of subgroups inductively. So the first subgroup, as the first term of this chain, we take the trivial subgroup. The second one, so Z denoted by Z1Z, is nothing but the center of the group G, and so therefore we are the term with index 0 is trivial, the term with index 1 in that chain is the center. Now assume that we have defined for n, we have defined Zn of G. Now Zn plus 1G is defined from Zng in the following way. So so as I said that assume that we have defined a normal subgroup Zng. We have defined a normal subgroup Zng of G. Now from G to Zng we have this quotient map, let's call it pi n. So we consider the center of the right hand side and then pull that center back to G and denote that by Zn plus 1G. So let me again repeat the construction for you. So Z0 is trivial, Z1Z is the center of G. Assume that we have defined a normal subgroup Zng of G, and from Zng we define Zn plus 1G in the following way. That is, we consider the quotient group G modulo Zng, we then take its center and pull it back to G by the quotient map from G to Zng, and the pullback of the center is denoted by Zn plus 1 of G. So thus we have the Zn plus 1G modulo Zng is nothing but the center of the group Z modulo Zn. So I mean it's quite clear from the construction that that E Zng is a normal subgroup of G. This is because so if we are given a group G and a normal subgroup N, then the correspondence theorem says that the subgroup of G modulo N and the subgroups of G containing N, they are in a bijective correspondence, and that correspondence also preserves normal subgroups. That is, the normal subgroups of G goes to the normal, a normal subgroup of G goes to a normal subgroup of G modulo N, and a normal subgroup of G modulo N, its pullback is going to be a normal subgroup of G. Therefore, we get each Zn is a normal subgroup of G, and Zn plus 1 modulo Zng is of course abelian, because it is actually the center of some group, and center of any group is always abelian. Okay, so thus this chain of subgroups obtained by taking successive centers in this sense. So we see that indeed gives us an abelian tower in G, because each subgroup is normal, and in fact the factor groups are abelian. So for any n, G, so for any m, this is going to be an abelian tower in G. Now look at the sequence, this increasing sequence, that Z0Z, Z1Z, Z2Z. So this series is called the upper central series of G. And if G is finite, then this chain must stabilize somewhere. That is, there should be some m for which Zm plus 1 Z, Zm plus 1 of Z should be equal to Zm Z. And once two consecutive terms become equal, then as a consequence, all terms from that stage and on, from the stage onwards, will be equal. So that is what we express by saying this chain stabilizes. However, there is no guarantee that when the chain stabilizes, the term will be the entire group G. That there is no guarantee in that. If that happens, that is that is for some n, for some m, Z and Z becomes Z, then the group will be called nilpotent. So so and the least integer n for which this happens is called the nilpotence class of G. So let me again repeat. So given any group G, the upper central series of G is obtained by taking the successive centers. So we define a sequence of subgroups inductively in this manner, and we see that for any n, that gives us an abelian tower in G ending with the trivial subgroup, and also this chain of subgroups must stabilize at some point if G is finite, and if it stabilizes with the entire group G, then the group will be said nilpotent. And the stage where stage where it starts happening, that stage is called the nilpotence class of G. So it is immediate that every abelian group is nilpotent, because you see that for an abelian group, since the center is for an abelian group, since the center is the whole group, so automatically apart from this term, so apart from this, all the terms, all Z1Z, Z2Z will be the group G itself. So it's trivial to see that an abelian group is nilpotent, irrespective of it is finite or not. And also, it's very natural to ask here that can we think of a non-abelian group which is nilpotent? Unfortunately, right now we are not in a position to answer that, but let me tell you that of course there are plenty of nilpotent groups. The class of nilpotent groups is strictly larger than the class of, in the category of finite groups. The class of nilpotent groups is quite large compared to the class of abelian groups. But right now we are not in a position to give even a single example. So we will come back to nilpotent groups later. But before we leave nilpotent groups, let's explore its connection with solvable groups. So since a nilpotent group admits an abelian tower ending with the trivial subgroup, so automatically the group has to be solvable. However, the converse is not true. An immediate example for this is the group S4. So S4 is solvable, but it is not nilpotent because center of S4 is trivial. So if the center is trivial, then you see that you are never going to achieve this, because that's clear from the definition that if the center is trivial, then G modulo ZG is nothing but G itself. So for the center is going to be again trivial. So pulling it back to G, then pulling it back to G again, you are going to get the trivial subgroup. So if the center is trivial, then there is no chance. I mean, then it is far away from being nilpotent. Okay, so S4 is a group which is solvable but not nilpotent. Okay, now let's move on to cyclic towers. So what follows in this lecture, we need to use the following, which I would leave as an exercise to you. So it just says that if we have a homomorphism from G to some group G prime, and then if a normal tower in G prime is given, then pulling the subgroups of belonging to that tower back to G, we get a normal tower in G. And furthermore, if this tower is abelian, then its pullback will be abelian. If this tower is cyclic, then its pullback is going to be cyclic. So I mean, so this result is quite natural to expect, and the verification is a routine on. Therefore, I am leaving it to you as an exercise. All right. Okay. So the next theorem says that if G is a finite abelian group, then it admits a cyclic tower ending with the trivial subgroup. So we prove this by induction on G. So if G has the order of G is 1, so we prove this by induction on the order of G. If order of G is 1, then there is nothing to prove. Otherwise, we choose a non-identity element in G and consider this factor group. So this factor group has order strictly less than that of G because X is not identity. Hence, from the induction hypothesis, we obtain a cyclic tower in the subgroups G modulo this cyclic subgroup generated by the trivial subgroup. So and then we use this exercise with F equal to the quotient map from G to G modulo X. If F is the quotient map, then the cyclic tower that we have obtained here, let's pull them back, and then the rest is just a routine verification that it indeed this indeed gives us a cyclic tower in G, and the tower so obtained has the last term as this X. Now, in order to finish the proof of this theorem, let us add one more term, namely the trivial subgroup to the tower obtained. By pulling the cyclic tower in G modulo X. So let me again repeat. So we choose a non-identity element X in G. That gives us, from the induction hypothesis, we do have a cyclic tower in G modulo X. Then we pull that tower back to G. So that indeed gives a cyclic tower in G, but it is ending with the cyclic subgroup X. We then further add the trivial subgroup to that. In this context, we leave the following exercise that every finite abelian group admits a cyclic tower ending with the trivial subgroup with all factor groups of prime order. This is a very straightforward exercise. So, and as an immediate corollary to that, one obtains that given a finite group G and a normal subgroup H of G, so here G may not be abelian. If G mod H happens, this factor group happens to be abelian, then there is a cyclic tower of this form. Okay, so we now move on. Just let me make sure I didn't miss anything here. So here we proved that a finite abelian group admits a cyclic tower with that which is ending with a trivial subgroup, and then we have left as an exercise that every abelian group admits a cyclic tower ending with the trivial subgroup, and furthermore all the factor groups having prime order. So let me again just say the difference. So here the cyclic tower, so here in the finite abelian group, the tower that you have obtained is a cyclic tower, but the factor groups may not be of prime order. So the essence of this exercise is we can further adding more and more terms if necessary. We can further enlarge the tower into a cyclic tower, of course, whose factors are of prime order. This is the essence of this exercise. In fact, what I just said, that with this tower we enlarge this tower by introducing more terms. This is called refinement. So let me make the definition here. So for a given tower G, a refinement for a given tower, by a refinement of this tower, a refinement is obtained by inserting finite number of subgroups in the given tower. Okay, so let me explain that by example. So I mean, suppose n is a normal subgroup. So suppose that n is a subgroup of G that which contains Gi plus 1, and n is also contained inside Gi. Then we can consider this tower. So this is just obtained by inserting another term, namely n, to this tower. So this is an example of a refinement of this tower. Another example of a refinement is that so here we have inserted n somewhere in between. So another way of inserting a term is at the end. So if we consider a subgroup H of the last term Gn, then inserting H into this inserting H here gives us a refinement of the given tower. And it's quite easy to see that. Suppose we are given a tower and we remove a subgroup from that tower, then if we remove a subgroup from the tower, then the former becomes a refinement of the later. Another example of a refinement is for any m greater or equal to m, if we consider the abelian tower of derived subgroups up to stage n. So this is going to be refinement of this tower of this tower. So given any m and m, so this is an abelian tower. This is an abelian tower, and for any n greater than m, for any n greater than m, the tower that ends with the nth derived subgroup is going to be a refinement of this. Yeah. So, now observe that. So here, for a refinement, we are just inserting some subgroups. So it may so happen that the subgroups that we insert, those subgroups may already be present in the tower. That is, if n equals to the Gi plus 1 or Gi, or here H is equal to Gm. So then, though we are inserting more terms, but actually, apparently it looks like the tower contains more terms, but it doesn't change the length, right? Because the inclusions, after inserting those inclusions are not proper. If the length increases, then we say that the refinement is proper, and if the length increases by 1, then we call it one-step refinement. So let me again explain that as I said here that from this theorem, the abelian tower that we obtain, the factors may not be cyclic. So by further inserting more and more subgroups, if we can enlarge that tower in such a way that now in the new tower all the factor groups will be cyclic. In fact, the factor groups will have prime order. So this enlargement of this act of enlarging a tower by inserting further subgroups is called refinement. Is called a refinement of that tower. So the formal definition goes as follows, and we explain that by some examples. So here in this context, I would like to give these exercises to you. So these are quite straightforward. That if you are given an abelian tower, then an abelian tower which ends with an abelian group, then if you refine that tower, then any refinement of the tower is going to be abelian. And so this is quite straightforward. And if G is a finite group, then every abelian tower ending with the trivial subgroup admits a cyclic refinement, having all non-trivial factors of prime order. So basically this is a combination of this exercise and this basically this is to do this you need to use this exercise. Because once an abelian tower is given, you have to refine that in a way. In fact, this is basically rephrasing this exercise, and then nothing else perhaps. The third one says that if G is a solvable group, then it admits an abelian tower with the trivial subgroup having all non-trivial factors of prime order. So this is also quite clear because in the second exercise it says that if G has we are given an abelian tower in a finite group G if we are given an abelian tower ending with the trivial subgroup, then it can be further refined to an abelian tower whose all non-trivial factors are of prime order. So if G is a solvable group, then of course we do have an abelian tower. That's what we have seen earlier. And then we using exercise 2, we can further refine that to arrive at this stage. Okay. It admits an abelian tower ending with the trivial subgroup having all non-trivial factors of prime order. That's true. Yeah. So here I think I need to make a small correction. So so I should here add that if G is a finite solvable group, so this condition is necessary here. Let me check whether we have to include that or not. So if this is a finite, because if you in order to apply the previous one, we need the group to be finite. Yes. So here this condition will be added that G is a finite solvable group. Okay. Anyway, all right. Now we are going to talk about an abelian tower of a very special form. So, like here, if you see that in the third exercise, or maybe in the second, that every abelian tower ending with trivial subgroup So if you can refine it and you can arrive it at such a stage that where you cannot refine further, because once all the factor groups have all the non-trivial factor groups have prime order, if you disregard the inclusions which are not proper, then if you disregard them, then you cannot, since all the non-trivial factors are already cyclics of prime order, you cannot further refine the given tower. So thus we are at a situation where we are at an optimal situation where we cannot go further. This is the main idea behind the following definition, which is known as the composition series. So for a given group G, a composition series is a normal tower with all factor groups non-trivial. That is, in this normal tower, we are only allowing the inclusions to be proper. Okay, we do not allow some gi to be equal to gi plus 1, because they are not actually giving us anything apart from increasing the number of terms. So we disregard such terms because they are completely useless to us. So it's a normal tower with all factor groups non-trivial and simple. So therefore we see that we cannot further think of any proper refinement. Okay. And so a series, an abelian tower of this form is called a composition series for the group G, and then the factors of this tower are called the composition factors of this series. Okay. So let me make the remark here that for any group G and normal subgroup N, the subgroups of G containing N and the subgroups of G modulo are in bijective correspondence, and the correspondence is sending each H to I'm sorry, I think I need to just make a change here. Yeah, it will be just M. So yeah, and the normal subgroups are paired in this correspondence. So it follows that if G modulo N is non-trivial and simple, if and only if N is a maximal normal subgroup of G. So what I mean by that is, of course, N is a proper subgroup of G, and there is no normal subgroup of G. There is no normal subgroup of G lying between N and G. So it's a maximal normal subgroup. So it's a proper normal subgroup, and I think I should make this. Yeah, it's a proper normal subgroup, and furthermore, there is no normal subgroup of G which is lying strictly in between N and G. So, in view of this, it is now immediate that a normal tower is a composition series for G if and only if each Gi plus 1 is a normal subgroup of Gi. Because this is equivalent to have each factor group is non-trivial and simple. Okay. So therefore, in the definition, we can equivalently say that each Gi plus 1 is a maximal normal subgroup of Gi. Let me give you some examples of a composition series. So this is an example of a composition series for D8. This is an example of composition series for S4, and so these are also compositions for the composition series for the same group S4. So this example show that given a finite group, first of all, we don't know whether it admits a composition series or not. That we don't know in general. But even if it admits composition series, then there is no guarantee that that composition series will be unique. For S4, we have seen 3 different composition series. However, even though we have 3 different composition series, we do have a similarity among these 3. So what is the similarity? What's the first factor group? This is Z modulo 2. The second factor group is Z modulo 3. And here the third one factor group is Z modulo 2 again. And fourth is also Z modulo 2. So here we have one Z modulo 3. So two factor groups, sorry. So, yeah, so we have one, the first one, third one, and the fourth one. So we have 3 factor groups isomorphic to Z modulo 2 and 1 factor group isomorphic to Z modulo 3. The same you can see here as well. So even if we have several composition series for the group, we have several different composition series for the group S4, still there is something very common to all of them. That's what we have seen in these examples. In fact, this is the content of the uniqueness part of the Jordon-Holder theorem, which we will be proving shortly. So before that, let's try to answer the question of regarding the existence of a composition series for any finite group. So given a finite group G, if the group is simple, then of course the group we start, we disregard the trivial case. So if the group is not simple, if the group is simple, then we don't have anything to do. We just stop. And therefore immediately we see that this is going to be a composition series. And if the group is not simple, then it contains a maximal normal subgroup, say G1. Clearly this has order strictly less than that of G. Now if G1 is simple, then we stop. If G1 is not simple, then it has to have a further maximal normal subgroup, say G2, and then we must have this. Since G is finite, then if we continue this way, at some stage we must stop, right? Because the order is decreasing. So thus we finally obtain a simple subgroup in this manner. And once we obtain a simple subgroup, it is quite clear that this is going to give us a composition series for G. Okay. Well, I think here there is a small error that we further need to add this trivial subgroup. Anyway, we further need to add the trivial subgroup if if Gn is non-trivial, then we further need to add a trivial subgroup. Otherwise, we can say if Gn happens to be trivial, then we can stop with Gn as well. Okay. So formally, try to understand that the way we argued that for a finite group, it indeed has a composition series. If we put that formally using induction, then that gives a formal proof of the fact that every finite group has a composition series. So let me again repeat that, as I said, that this is a formal induction proof. So the strategy of proof is very natural, that if the group is simple, then we'll stop. Otherwise, we look at its we will look at its one maximal normal subgroup. Then if that subgroup becomes simple, then we stop. Otherwise, we go ahead, and then proceeding in this manner, we have to arrive at a stage where the subgroup becomes simple, and that immediately yields a composition. That immediately yields us a composition series for the finite group G. And so this is what the line of argument is. Putting this in formal way, we got a formal proof of the existence of a composition series for any finite group G. Now let's come to the issue of uniqueness, which I was talking about, that a finite group may have several different composition series. So here if you see that we have seen the 3 different composition series for the group S4. However, though the series may be different, but there is some sort of uniqueness in terms of the composition factors. So we need to make that precise. So this is the content of Jordon-Holder theorem. It says that let G be a finite group and let this and that be 2 composition series for G. Then, for a composition series, since all the inclusions are proper, so the number of terms is exactly equal to, so 1, 2. So for simplicity, from now onwards, instead of 0, let's start with the index 1. Let's start indexing with 1. So thus this composition series has n plus 1 number of terms, so that its length is n. Similarly, this composition series has length m. So the Jordon-Holder theorem says that for a finite group G, if 2 composition series are given, then first of all their lengths are to be same, and furthermore the factors of the first series, the composition factors associated to the first series and the composition factors associated to the second series, they are same, of course, in the sense of isomorphism up to some permutation. That is, for some permutation of 1 up to n, so the composition factor here is isomorphic to the composition factor like this. So in simple terms, if we are given 2 composition series for the same finite group, then their lengths must be same and the composition factors are same up to some ordering. Here same is again in the sense of isomorphism. That's what Jordon-Holder theorem says. And as an immediate corollary of that is a finite group is solvable if and only if its all composition factors have prime order. So earlier we proved that a finite abelian group is if a finite abelian group is solvable, then it has an abelian tower whose all non-trivial factors are of prime order. Now from that abelian tower, if we remove those subgroups which are redundant, then we arrive at a composition series whose all factors are of prime order. Now Jordon-Holder theorem says that whichever composition series, the Jordon-Holder from the uniqueness part of this Jordon-Holder theorem. So from this uniqueness part of this Jordon-Holder theorem, it say we obtain that whatever composition series of this form that we consider for a given finite solvable group, then the composition factors are going to be exactly same in the sense of isomorphism. So therefore, we obtain this corollary. So this is, as I said in the beginning of this lecture, that we will view solvable groups from a slightly different perspective. So this is an equivalent criteria of solvability. That is a finite group. A finite group is solvable if and only if all composition factors are of prime order. I hope the point is clear. If not, I can explain once again. That earlier we proved that given a finite solvable group, it admits a tower, an abelian tower, whose all non-trivial factors are of prime order. We remove the redundant terms from that tower, and that gives us a composition series with all factors of prime order. The primes might be different, but the main point is the factor groups will have prime order. Now Jordon-Holder theorem assures that we do not, Jordon-Holder theorem assures that we cannot have another composition, we cannot have another composition series whose factor groups are different. Okay. All right. We now need to prove the Jordon-Holder theorem. So, as most of the theorems of finite group theory, we will also prove the Jordon-Holder theorem by induction on the order of G. So we consider the following two cases. So suppose these are two if these are two given composition series for G, we first split our argument into two cases. In the first case, we deal with the situation when G2 becomes equal to H2. What's the advantage for that? If G2 is H2, then this and that both are clearly composition series for the same group G2, which is same as H2, right? So if G2 is H2, we simply disregard the first term from both the composition series for the time being, and that gives that we have two composition series for the same group G2 equal to H2, and of course G2 has order strictly less than that of G, and then induction hypothesis takes care of the rest. So we obtain n-1 equal to m-1, and a permutation of 2 up to n plus 1. And a permutation of just a minute. Okay. And a permutation of 2 up to n plus 1. Yes. I'm sorry. Just there is just, I need to make sure something. Yeah, there's a small error. Yeah. So there is a permutation of 2 up to n such that the factor groups from this stage onwards and the factor group from this stage onwards, they will be same in the sense of isomorphism, and this permutation is extended to a permutation of 1 up to n by setting sigma of 1 equal to 1, because the factor groups appearing here and the factor groups appearing there are same in the sense of isomorphism up to some ordering, and the first factor group, this G1, this G modulo G2 is same as the first factor group of the first factor group, the first factor group of the first original composition series, and the first factor group, the second given composition series, they are same. So that is one. Therefore, once we extend this sigma, to sigma to 1 up to n by setting this, we indeed we prove the desired conclusion. Okay. So again, let me repeat. So the factor groups appearing here, and the factor groups appearing here are the same. So if we want to get back to the original given composition series, so only one factor group from either of them is left, and since G2 equal to H2, they are already the same. Okay. All right. Now let's come to the second case. In the second case, we assume G2 not equal to H2, and since both G2 and H2 are maximal normal subgroups, so maximal normal subgroups of G. So here I should have written G, or subgroups of G. Anyway, so therefore their product, which is of course a normal subgroup, and since they are not equal, so it will be a bigger normal subgroup containing G2 and H2 both. Hence G to H2 must be equal to G, And then we use second Desmorphism theorem to see that G modulo G2 is nothing but H2 modulo G2 intersection H2, and similarly G modulo H2 is this. So this shows that the subgroup K3 defined to be the intersection of G2 and H2 is a maximal normal subgroup for both G2 and H2. Because this since this is non-trivial and simple, so this being isomorphic to this also has to be non-trivial and simple. So thus K3 is a maximum normal subgroup to both G2 and H2. Alright. So yeah, so now to consider a composition series for K3. This exists. We have already proved that for any finite group there is a composition series. So once you obtain a composition series for K3, then that leads to the following 4 composition series. So the first one is the first and last in this list are the given ones in the theorem, and the second composition series is so G1, G2. Then we continue with the composition series for K3. Similarly, here also we can do the same. So these two are composition series. These two are indeed composition series in view of the fact that K3 is a maximal normal subgroup of both G2 and H2. So thus we are having 4 apparently different composition series. And we now start comparing this series. So we can immediately compare the first and second composition series. It actually reminds us the previous case. That is, in these 2 composition series, you see that the not only the first term in that composition series first terms are same, also the second terms are also same. So we exactly come back to case 1. So therefore for these 2 composition series, we can say that their factors are same up to some ordering. The similar argument goes for the third and the fourth one as well. So yeah, so yes, so comparing the first 2 composition series, we obtain n equal to L and permutation such that gi modulo gi plus 1 is isomorphic to k sigma I modulo k sigma I plus 1, k sigma I plus 1 for all I, where we have defined K2 to be G2 for the simplicity. And similarly, similar things holds for the third and the fourth composition series as well. So now we have to do the main part. We have to do the main task, that is connecting the second and the third. And using that we will finish the proof of the Jordon-Holder theorem. So again, let me remind you that the composition factors of the first one are exactly same as the composition factors of the second one in the sense of isomorphism up to some ordering. Similarly, the composition factors of the third and the composition factors of the fourth are same, of course, up to ordering. And we see that if we compare the second one and the third one, so from this point onwards, all composition factors for both the series are same. Okay. Let me repeat that if we now focus on the second and the third, the composition factors from this point onwards will be same for both the series. So now the only factors which are left out is G1 modulo G2 and G2 modulo K3. So, and here H1 modulo H2 and H2 modulo K3. So now let's recall that G1 modulo G2 is nothing but H2 modulo K3. So G1 modulo G2 is H2 modulo K3, and similarly here we have G2 modulo K3 is actually corresponding to H1 modulo H2, that is G modulo H2, we seen it here. Therefore like if in this two composition series we see that all the composition factors are same, and combining this with the observations made for 1 and 2 and 3 and 4, we see that all the composition factors of the first one and the fourth one, they are the same up to some ordering. Let me again repeat this argument. So first we compare 1 and 2, then we compare 3 and 4. Now the main task is we have to connect our observations obtained for 1 and 2 and 3 and 4 by comparing the second one and third one. So the composition factors of the first one, which correspond to the composition factors of the second one up to this point, they automatically those factors will appear here as well, and automatically those factors will correspond to some factors in the fourth one, and the only things might be left which correspond to these two factors, and that's not an issue because this factor, the factor G1 modulo G2 is isomorphic to this, and this is isomorphic to that. Therefore now all the factors have been considered. So that's what is put in this way, that for 2 and 3 the factors ki modulo ki plus 1 are same, and the first and the second composition factors of 2 are isomorphic to the second. So first and second of 2, the first factor and the second factor are isomorphic to the second and the first factor of 3. Therefore putting everything together, now we prove the Jordon-Holder theorem. So yes, so let me just explain what this theorem says. The theorem says that, so we have already observed that given a finite group, it has a composition series always, but it may have several different composition series. So though they are different, however, there is some uniqueness, some sort of uniqueness in terms of the composition factors in the following sense. That is first of all, the lengths cannot be different, and the factor groups up to factor groups, they cannot be isomorphically different. Okay, so if we are given two composition series for a finite group, then the factors of the first series and the factors of the second series are basically the factors of the first series. The factors of the first series are basically reordering of the factors of the second one. Okay, of course here the sameness is considered in terms of isomorphism. So isomorphically we cannot have different factors, and as an immediate corollary to that, we obtain this criteria for solvability for any finite group. Okay, so with that I will finish this lecture.